Okay, you're going to do biochar. You've explained with it. One day you decide, let's do this, and you order a truckload, and now this is what happens. This is a bulk load. So you've got 100 cubic yards, 80 cubic meters, 75 cubic meters. It shows up. Yeah, you have a place to put it because you'll be picking it back up. But you soon realize that there is an enormous amount of material that has been delivered to your place. So back up a little bit. And when it gets done, you come to the realization you have essentially a pile of material that you have some information about, but you lack for specifics. This is probably what you know about the material at this point. You know what you paid for it. You know it showed up at the right place. You have a number of facts, let's call them details that the seller promised you, and then how much he sent. But you really lack the details you need to go forward effectively to incorporate this material into either the soil or some other application. I want to introduce a concept that is pivotal to biochar. It is density. Density is a very broad concept. It's basically how much of something is in some other unit of measure of that something. So it might be weight per unit volume. It might be amount of stable carbon per truckload. It can be whatever you define it as, but it is the key relationship that lets you go back and forth between volume and weight of the material. And as you're using biochar, typically you're dispensing it as a volume. You're picking it up with something or put it into bags or somehow moving it around. But you need to know the amount of actual material held in that volume, and that varies depending on a number of things. Here is an example of measuring, and what some people may accuse as a crude way, but frankly, any data is better than no data. This is a measurement of as-made biochar. There was a ring kiln event that they made the char. All you need, and on the left is a way of weighing something and a device to hold the volume. And you tare it, subtract away the starting weight that's not biochar. Then you obtain some kind of representative sample. That can be more of a challenge depending on the application. And you weigh it. So because there was no water added to this material, they would call this the bulk density, the weight per unit volume of whatever the bucket volume is, of the as-made biochar. So it seems crude, but frankly, it's not. And there's reasons for that, which is it's not hard to measure density, but it's hard to measure density to many significant figures, and I'll show you. But before we jump into methods, let's think about biochar as consisting of four major types of materials. There's the ash, which is can come with the starting raw material to make the pyrolysis. It can come in with dirt on the wood if they made it from a whole tree chipped or something. Then you have what we call I call the resident matter, the mobile matter. This is the carbonaceous material, the organic components. There's a lot of names that get used. I, way back in the day, tried to use resident matter, meaning the stuff that tends to stay where it is in the soil. In mobile matter, the material that tends to migrate either into the groundwater or somehow disappear. It's not there 5 years from now. And then there's water. And I changed the titles because I didn't want to be confusing them with calling it, say, volatile matter, which now is a term of art in the coal industry and other names. But unfortunately, there is quite often quite a bit of confusion as to whether you're using a defined phrase, volatile matter, or a imagined one like labile matter. So the key to understanding biochar is to break that four components into their separate measurements. And the first one is to get rid of the water. And the reason was that the water is added after the material is made, so it can be a very arbitrary amount. But let's start, before we start trying to peel it apart, let's start with as is. And therein lies your first layman science step, which is get yourself a vessel that is calibrated. In this particular case, we happen to have a canning jar, which has the milliliters written on the side. Not a lot of significant figures, but we won't need those. Again, it's a sealed material, a container, because we're going to grab a sample as is and seal it up so it doesn't lose moisture in the before we measure the other properties. And the other thing I want to note, and I really urge you to take this jar of material, do some measurements as you take small amounts out to test things, but put that jar on the shelf and keep it for forever. Well, a long time, because if the biochar doesn't work correctly, well, maybe you want to do additional testing on it to find out what didn't work or what was missing. Or if it really worked great, then again, we need to be measuring it to get the specifics to try to match it. So it is important to have a retain, because once it's in the soil, you won't be able to get a pure sample back. So this is really what you got in a truckload. And importantly, this is the recourse you have if the truck doesn't match what you were promised. So the guy said it's less than 5% ash. You measure this material, it is 30% ash. Well, now you've got data to go back and ask for some settlement or something. He's not going to take the load of char back, but you might be able to get to some parity on what was promised, what was sold, delivered, and paid for. This is a sample of a typical biochar. So if you noted, we have a tear. So we weigh the jar clean and dry. We write it on the label. We have a scale somewhere. And the interesting thing about biochar is its particle sizes are such that it'll settle somewhat like cereal, and it'll also fluff up. So the amount that was in the truck was a smaller volume than the amount that was dumped on the ground, because in the process of being dumped, it fluffed. It expanded because it didn't pack as nicely. So here's the two measurements. The one on the left is fluffed up the jar. You just literally shake it up a little bit and let it stop. And it's got a calculated density of 0.3231. That would end up being kilograms per cubic meter or grams per centimeter cubed here. And then if you settle it, just literally kind of, jostle the bottle a bit and let it pack down a bit, it'll rise up to 0.249. Now, I'm carrying three significant figures, but you can see they bounce around so much. Really, density is a two significant figure number, but two is better than none. I think you can appreciate we haven't worked very hard so far. We have a scale of some quality, which we can buy off of eBay for a very low price for the number of significant figures you need. You do need, if you're going to use that jar, you're going to need 2 to the 100th of a gram. but it's not a big investment. And if you're going to be using biochar, if you're going to be trying to be sort of making decisions based on the input, you need to have a modicum of small scientific method and equipment, of which apparently canning jars and low cost scales are part of the game. Here is the next step. We want to take the water out, and the water in biochar can be anywhere from almost minimal, not quite bone dry because it absorbs from the air, but it can be up to 3 and 4 times the weight of char because it has so much voidage. And herein is the apparatus that was used for many, many years by me, is to dry the material out. And we need to be essentially what is called bone dry, and that means we've taken away the absorbed water also, and that's done at 150 degrees C, not 104, like the drying oven in every lab. And that's another precaution. Many times when you send a sample of your biochar off, they dry it at, quote, 104. They dry it, quote, and that's at 104 degrees C with all the glassware, because that's what glassware is dried at in the lab. And that has a flaw. It doesn't remove absorbed water. Here's an example many years ago of taking samples and drying them at 104 degrees C or 100 degrees C, thereabouts. And you can see, depending on how much water there is, this is weight loss. So the one minus this is the actual amount of dried material. But these chars all had between 25% and 75% moisture. And the 75% moisture sample, which is not an outlier, it was char that came in a truckload, had, it took hours. It took 18 hours. So if the lab throws it into a drying oven for 2 hours, you're going to leave stuff behind. And this is, we're going to shift slowly to instrumentation to do this work. And this is an example of what the instrument sees when it dries a 1 gram sample of that biochar. Well, actually, this is probably an activated carbon because I'll tell you, we use that for a reason as a calibrating standard. But you can see that at 100 degrees C, it comes down in weight quite quickly, but it leaves a heel for a very long time. And the pink purple line is the temperature. It's oscillating because it's a very, very accurate measurement of temperature, and it's bounces around. But you can see that at 150 degrees, when we go up to the next to the higher temperature, the weight comes off very rapidly and is stable. So this is the apparatus that I'm going to use to create the data that goes on. Now, this is a new apparatus. I developed this recently in the last year or so. It's a modification of the one I've used in my lab for decades. And it's essentially a gravimetric analyzer, or a TGA, as they're called, thermogravimetric analyzer. And there are not many of these out there, so maybe it's unfair that I'm making data on this, but I want to point out what the data can tell you, and then you can decide whether you want to pursue this instrument. I'm making and selling the instrument complete now within continental United States. And there are not a lot of them out there, but hopefully they'll catch on, but we'll see. It's a situation now where you won't not only be the first one on your block to have one, but you be the first one on your continent. So this is an instrument which, if you look in the upper right, it takes a sample of your material in a very small mesh basket, hangs it below a scale, and then the data subjects it to a flow of laboratory nitrogen, bone dry nitrogen, and records the weight every 30 seconds and collects a lot of data on what the conditions did to your material. One key feature of this modified TGA or custom TGA is the sweep gas going up through the sample, removing any desorbing volatiles or vapors, and that's to prevent additional pyrolysis from making additional char, which wasn't there in your sample but might be there during your analysis. Again, a situation that is a problem with existing TGAs, that they have usually covered or not flushed samples, and therefore you don't have good removal of the volatiles and you have secondary carbonization, etc. So this is the reason we do, I don't know if I mentioned it, but we're going to do our ashing to remove the ash. So we're done with the water. We got the water off either with the modified or absconded with, let's go back and take a quick peek at that. This is nothing other than a toaster oven. On the left is a slightly better thermal control device. But to be honest, the toaster oven is close enough. We're trying to dry it between 140 and less than 200. And we're trying not to strip the volatiles off, which is the reason we have foil over the top of the jar or a lid on the crucible. And we can do drying in this thing, as we'll see. But switching to ash, you've got to ash below 5 or 600 degrees C, critically. And this is an example where pure calcium carbonate, which is a typical ash component in your biochars, is stable at 550 C for 6 hours. At 650, it slowly degrades. At 750, it frankly falls apart and leaves just calcium oxide. And then upon being taken out back to room temperature, it proceeds to start taking up atmospheric CO2. So if you want to measure the calcium carbonate as calcium carbonate, you've got to do it below 550. And this is a real issue with labs that measure ash with the ASTM test, which is a coal-based test. Whether it comes on a piece of paper that says charcoal or not, it is developed around coal, is that it decomposes all the carbonates into calcium oxide and magnesium oxide. And now that makes a lower ash measurement. And you really end up attributing that lost CO2 to some other class, typically the carbon class, the organics class. This is an example, and I've written this up in earlier talks, of how you can do ash by taking the tops of those little crucibles and putting it in a muffle furnace. Now, you need for 500 degrees C, which is an intermediate temperature than the typical ashing that's called for, which is, I don't know, 900, 750, some ridiculous number. It's still, almost 1,000 degrees Fahrenheit. It's a very difficult temperature to hold accurately. So a muffle furnace or some other device is intended. And the instrument, which is nicknamed GACS Plus, GACS Plus, does go to 500 degrees C. This is an example, and I'm going to go quickly through some data that'll be more representative of the kinds of data. This is a typical ash sample. You can see in the upper left, we take the sample, put it in. It very quickly, at about 150 degrees C, loses the moisture, becomes stable. Then we ramp up, and in the course of the ramp in air, we see the oxidation, but it's very uniform. It doesn't start combusting, glowing red, giving off flames, all of which would be fine inside a little tiny instrument. And then it stabilizes, and you've got the residual ash. And it is totally ashed. This is an example of a very high ash material. You can see it, you'll measure the ash content by doing the math off the two plateaus. And this is an example of a material that's a very low ash, ended up being calculated to be about 1%, which is artificially low for most biomass-based biochars, because the starting material had, a 0.5% ash in it, and you concentrated it up as you carbonized it to concentrate that ash to typically something in the plus 2% range. But these things are possible, and it's, again, a very good insight, and this would be astonishingly clean char. So don't look a gift horse in the mouth. And the good news and the bad news. We've really only characterized that little right-hand piece. We don't have, and here's where they're using the old names, fixed carbon and volatile matter, which come from coal characterization. And we're going to take a stab at trying to pull those two groups apart. This reference, this particular piece of work is the finest piece of work that's out there so far, out of the UK, out of Christian's group. These are his colleagues, and it's really to be admired. I also admire their comment at the bottom. Approximate analysis has its root in fuel chemistry. It was used to determine the macromolecular composition of a substance at operational temperature, 1,000 degrees C. So it's not designed around biochar. Back to what we started with, we have a way of removing the water from the sample before we do additional tests. We have a way of quantifying the ash. Now we're going to take a look at how we might partition the organics, which are the green and red portions, into something we can interpret. And this is what I have determined to be the best starting place, which is, let's break the organics. Let's use this instrument to strip off the VOCs, and then at a higher temperature. So we start drying in red there at 150. We go up to 300. We hold it for a fixed period of time. And I've fixed that as an hour just to be standard. And then we go up farther to 450 and higher boilers come off. Are these rigorous partitionings? Not until a lot more data by other people come in, but they are at least reproducible ways. And what we've got with all this data is a series of high temperature chars that are, losing relatively little VOCs and SVOCs, down to that bottom line, a 350 C char, which has an awful lot of VOCs and SVOCs coming off. So we're seeing a different response as a function of how much can be stripped from the material. It relates for this group of chars to the temperatures they were made at. You don't really know the temperature of the char and that you bought. He'll tell you, oh yeah, it's a 600 degree C char, but de facto it could be whatever. Again, just measuring it and knowing how it behaves. And in this case, what we're measuring is what's going to come off. VOCs are typically what tends to come off into the soil. It's a source of carbon. For the microbes, it has some nitrogen consumption associated with it, but it also might develop microbe populations if you have a low microbe soil. And then SVOCs, these are materials that are much higher boilers. They may or may not last a century. Again, more data is needed. But an instrument like this does a very nice job of pulling them apart for any sample you put on there. Here is an example, and this is activated carbon. Why did we pick activated carbon? Oh, no, it's not. It's I can't read the title anymore. This is a standard carbon that I use that is nice because it tends to have a little bit of everything in it. It's got a lot of moisture that comes off. It's got VOCs, that middle swoop, and then SVOCs. And then at the bottom, when it cools off, you actually see some temperature, some weight gain, and that's because the balance is being influenced by the temperature underneath it. Not a huge drift, but something you can see. The nice thing is I put the sample in, I punch a button or set up the run, and it just does it over the course of several hours. The other feature that's very, very useful is on the way down, from whatever temperature you were at, you can then measure the absorption of the material. And that's done with a challenge gas, either propane or R134A. And I'll wrap up quickly here to get the questions. And so you can measure the absorption on the sample after you've modified it by stripping off some of these materials because they sit in absorption sites, and you'll see the improvement. So here's a table of data. This is the kind of volume of measurements that you get out of a single run. Here's the gold standard, I call it. It is a very high quality material after you strip all the VOCs and the SVOCs out. And and you can see a number of the measurements and the data reduction. I've got not only the actual loss of VOCs, and that was that data here, created that table of data. The raw data gets, you do the calculations based on the measurements of the raw data. We removed a total of 24% of the sample's weight after drying at those two temperatures. That's a lot of material. We need to fill in with some additional cross calibrations with other measurements to see, what that's implying. So you have not only a total weight removed, you have a weight per hour, a rate of weight stripping. It's for the initial hour. Again, these are just reproducible measurements that are going to let you compare it to other chars. And here's a couple of examples of the intermediate chars. The GAX at 150 is just dried, and then we measure the absorption. And then 300 some material came off. We removed 7% of the VOCs, and we saw the absorption dramatically leap up, which tells us the VOCs are in the absorption sites, which has a couple implications, but I don't want to divest into them into speculation. So on a typical absorption plot, we're seeing the red line is that 150 material, and then the stripping of the VOCs moved it up to the purple line, and then the 450 took it up even further. And we're seeing the migration of the absorption properties as we modify an actual sample of our actual char. So summarizing, the underlying idea is you got a shipment, you've got a char, you're either making it or bought it and you want to use it. We need to take that material and into the lab, measure some properties of the sample you've got to now steer how you're going to use the material, or if you're making it, how you're going to modify the production for properties you're looking forward, you're looking to have either higher carbon, less dissolvable volatiles. Maybe you want to make volatiles because you've got sterile soils and you want to build up some microbial population. And I'll give you back my screen. That still remains me. And it's back to Christian, and let's take whatever questions there are. I'm sure there'll be some. A lot of people I recognize. And that's the GAX Plus instrument tearing apart samples of char. And Christian, you're welcome to take the screen back and do your magic.
Yeah, I'm here. Thanks you. Thanks for the presentation. I also like the video. So was that your shipment or?
Oh yes, the reason I was videoing that is that's the first bulk load I had. And I went and bought the largest tarp they sell at Harbor Freight, and I put it down, and I said, this is going to make my life so much easier. And we spent, literally days out there trying to load it into super sacks to sell it to people and to test it and stuff. It's a really sinking feeling in your stomach when that load drops and you realize that, it's exposed to the wind now. I was thinking, well, I'll put a tarp over the top of it to keep it protected. None of that happened. So yeah, it was my load. Very, very affordable, quite the bargain, but sitting there smiling at you. I had a colleague who ordered 5 yards bulk of biochar, and he had one of those driveways that was like a split level. So the driveway had kind of walls on each side. And the guy backed in the front of his garage doors and dumped 5 yards of char. He couldn't park his car for a week. He had spent a Saturday just wheelbarrowing it out back to his garden. So yeah, it's in bulk. It could be a challenge depending on how much there is.
And I think I'm going back to the content of your presentation. I think one point that you jumped a bit over is um, maybe you can quickly give us a very short answer on that. But how do you get a representative sample of your?
Oh, what an excellent question. Well, I think the first place to look for it is how was it made? And really, if you are, most of these, like bulk loads, are usually made by a manufacturing process. That particular material was a byproduct from a wood-fired power plant. And so it tends to be the same material. But to be perfectly honest, you've got to kind of, you've got two choices. One, you can assume it's homogeneous, just grab the first jar full. Two, walk around and take a snippet from multiple locations and add them all together and make a composite. You've got to basically give it its best shot, but biochar is a heterogeneous material and you're going to, have to deal with that. You could take 5 different samples and measure them all and see how much it bounces around. I think as you go on and further work with this material, you may want to take samples of individual batches you're selling or about to use and test that. But again, you've just you've got to start somewhere. But that is a huge challenge, and the ASTM method for it is to spread it out uniformly. Break it into 5. Take a sample from each quadrant, throw away the 2 in between, mix it up all again, spread it all out again. Well, you'd be, it's something ridiculous like, 20 individual grabs have to be taken from the material. So it's a huge challenge, but do the best you can. That's all I can offer you. Char tends to be more uniform than perhaps we think it is, unless you haven't ground it up yet. So if you're
Mhm.
coming out of those ring kilns, it's all over the place.
And Manolis was commenting that there are ISO standards for solid biofuels, including the sampling, but that's exactly what you just mentioned, that they are
Yeah, it's
very,
it's it's astonishingly labor intensive,
yes.
to get. And they did the studies to show that unless you go through this ridiculous challenge, you're going to have a very difficult time meeting their criteria. I actually urge you to take 5 different samples and test them for maybe moisture, because that's the one that bounces around a lot. If the moisture is aligning up, it's pretty homogeneous. You're going to have to go there to meet the ISO criteria, which is really a laboratory research standard. Is a high bar.
So Rajiv was asking, so as a biochar producer or commenting as a biochar producer and working with standards, for instance, the CSI, they need to send samples of biochar to accredited labs, but they have some, or they, it would be great to have a session on interpreting these lab results. And I think that's a question that comes up often. What's your comment on useful results from the typical EBC standards? What is
Well,
the
I'm in the States, so we tend to not have the EBC criteria.
or the IBI?
That's fine. That's fine. But I have published comparisons, and there's not only an issue of the laboratory's practices, but there's also an issue of them flat out picking the wrong test.
Hmm.
I believe EBC dries at 104 degrees C.
Yes.
And, you can tell the lab you got to dry to constant dryness. But if you go read Lehman's papers very closely, they dried a biochar sample in one use at 104 for 18 hours and never met the criteria. So they just gave up at 18 hours and used the number. So, this is the other problem with, first off, I want to comment. What we're doing here is we're measuring real time data on your char that you're about to use or you just made. That's a little different than sending off a sample to a lab for the purposes of getting carbon credits issued or something like that. They have their criteria of how much data they want and what kind of data, and you're going to have to meet that to get your credits. But let's imagine you take your child into his pediatrician. He's sick, and you say, I think he's sick. He seems to have a temperature. And the doctor looks at you and goes, Yeah, I measured his temperature 3 years ago. It was normal. Well, you're not going back to that doctor. And this is the problem. A lot of times, these EBC criteria, these are one time measurements, and these numbers are applied to many, many batches going forward. And frankly, a lot can change. So I think there's a lot of room for error to creep in to the IBI EBC kind of methods, either the wrong method or the wrong, property being measured and applied to your material. My focus here is to try to take properties directly from the material to give you interpretations and allow you to compare them to other materials you're working with and decide, if they're the same or different. And that's different than issuing a certification by a third party lab to get issued carbon credits. Just, you know,
Basically,
uh,
but
it's a scientist's approach as opposed to a institutional or regulatory approach.
I mean, you're doing basically quality management system, right?
Yes, you are. For a person running a kiln, this would be an excellent quality management thing. The water bounces around so much on biochar loads that really you have to decide how much water's in there to even know how much char you've got. The concept of getting even a bag of char and not measuring the water and then start putting in so many liters per square meter or something is really fraught with problems. Although I will note, in its defense, biochar volumes are relatively stable. They don't really, it doesn't swell and shrink a lot when you add water to it, so it's not bad. The wet char and the dry char are pretty much the same volume. The density is very different because the moisture's been removed. So the density term on top, the weight, the mass is bouncing around based on water removed.
Um, and one question from Vera Bodo or Vera Bodo. He might have missed it. Is there a simple way to get surface area? Because I mean, the more classical approach, I guess, he means.
Yeah, what you just did is ask, it's kind of like the equivalent of asking the Pope what his favorite religion is. I have spent decades railing against surface area. It is not appropriate for biochar. It is related or could be correlated to that absorption with the challenge gas, but that's a default correlation. But yes, if you do the challenge gas, either propane or R134A, there is a correlation. It's roughly, and I'm going to say roughly with as many disclaimers as possible, 50 meters squared per gram for each percent of absorption weight uptake. So if you had 10 weight percent R134A, which is a high quality char, you'd have the equivalent of about 500 meters squared per gram. But that, again, the problem I have is that the one single number really doesn't tell you enough about that material to tell you how to use it. But people do, in fact, flock to surface area. And earlier talks get into this. Now, the guys that invented BET nitrogen noted this is not appropriate for use on microporous materials, i.e., the stuff we're making. So when the inventors say don't do this and then the industry does it, well, I'm at a loss. But there's a correlation. There's a correlation in everything.
Yeah, I completely agree with you. I wrote a paper about the BT issues of BT as well. Yeah.
Oh, please post at some point the origin so I can read it and the whole rest of the world can read it. And you and I we can be burned at the same stake back to back. It'll be fun.
I think we are very far over time by now.